For easy realizing logarithm, it is better to understand application example rather than definition. 10 to the power what value is equal to 100? The answer is 2. So we can say 10 squared is equal to 100. Let's try to define logarithm with the help of 10 squared equal to 100. This equation. The logarithm of a positive number is the exponent indicating the power to which it is necessary to raise a given number, that is base, to produce the number. In this case, the base number 10 is to raise to 2 to produce the positive number 100. The logarithm with base a of m is equal to x if a to the power x equal to m. So we can say for the above case 2 is the logarithm of 100 to the base 10 because 10 squared equal to 100, which is written as log 10 base 100 is equal to 2. When we write this equation 10 squared equal to 100 in logarithm form, this 10 is the base of logarithm. This 100 is that positive number and this 2 is the value of logarithm. So we can say log 10 base 100 which gives the value 2. The conversion between the exponential equation a to the power x equal to m and the logarithmic equation log a base m equal to x. This a is the base of exponential equation as well as the base of logarithm. This m is that positive number of which we want to find the value of logarithm, and this x is the value of logarithm of log a base m. Now the fundamental formula 1. With the condition a greater than 0 and a not equal to 1, log a base 1 is equal to 0 because we know a to the power 0 equal to 1. Since a to the power 0 is equal to 1, so we can say log a base 1 is equal to 0. Or if we converted the equation log a base 1 equal to 0 to an exponential form, we can easily get a to the power 0 equal to 1, which is true for the value according to the given condition a greater than 0 and a not equal to 1. Why the condition a greater than 0 and a not equal to 1? Because if the 0 is raised to anything is always 0. And similarly, if 1 is raised to anything is always 1. Every negative number as a base of exponential function is not always real. We know the square root of negative number is not real. Then the fundamental formula 2 with the same condition a greater than 0 and a not equal to 1, log a base a is equal to 1 because we know a to the power 1 is equal to a. This one is always true. That's why log a base a is equal to 1. Fundamental formula 3. A greater than 0, a not equal to 1 and n greater than 0. In this case log a base mn is equal to log a base m plus log a base n. That is, the logarithm converted the multiplication form of number into the addition. Why the condition a greater than 0, a not equal to 1, m greater than 0 and n greater than 0. If the base of exponent is positive, then the value of exponent is always positive whether the power is positive or negative. That's why this m greater than 0 and n greater than 0. For example, 2 squared is equal to 4. Here the base is positive and the power is positive, which gives the value positive. And the next case 2 to the power minus 2, which is 0.25. Here the base is positive but the power is negative. Although the power is negative, this 2 to the power minus 2 gives the positive value 0.25. That's why this condition m greater than 0 and n greater than 0. The fundamental formula 4 for the same condition a greater than 0, a not equal to 1, m greater than 0 and n greater than 0. log a base m by n is equal to log a base m minus log a base n. This is the formula where logarithm converted the number which are in division form into the subtraction form. Now, fundamental formula 5. With the condition a greater than 0, a not equal to 1, m greater than 0 and n greater than 0, log a base m to the power r, which is equal to r into log a base m. When we simplify the equation log a base m to the power r, which gives the value r into log a base m. Note for this formula, that is log a base m whole to the power r, which is not equal to r into log a base m. Now, the fundamental formula 6, which is called the base change formula, that is log a base m, which is equal to log b base m divided by log b base a. With this equation, we can change the base a to the new base b. Here, this b is new base and this m is directly goes here and this a is here. So, we can say log a base m is equal to log new base m divided by log new base a, log new base of old base. So, application of base change formula. Now, we want to change the log 0.1 base 10 to the new base 10. According to formula, which is log 10 base 10, that is this 10 is the new base. We want to convert the previous logarithm into new base 10, that is 10 base 10 divided by log 10 base 0.1. This 10 is directly here, that is log 10 base 10 divided by log 10 base the old base, that is 0.1, which gives the value 1 divided by minus 1, because the value of this logarithm is equal to minus 1. How this 10 base 0.1 equal to minus 1? Because we can write this 0.1 as 10 to the power minus 1. Then this minus 1 we can write as a multiplication form, that is minus 1 into log 10 base 10. We know the log 10 base 10 is equal to 1, so the final value gives minus 1. Now, the finding value problems. In case of logarithm, the unknown value may be here or here or here. So, we just discuss here 3 cases. First one, log a base m equal to x, that is the unknown value is here. So, let's see one example. Log 2 base 4 is equal to x. Here, for 4, we can write 2 square, and according to the formula, this 2 we can write as a multiplication form. That's why 2 into log 2 base 2, which is equal to x, that is log 2 base 2 is equal to 1, so 2 into 1, which is the value of x, so x equal to 2. Next one, the unknown value is here as a base of logarithm. In this case, let's see one example. Log x base 25 equal to 2. What is the value of x? So, if we converted this logarithmic equation into the exponential equation, we can write x square equal to 25. How? This base x is here. This 2 as a power of this x, and this 25 is here. After solving, we get x equal to plus minus 5. So the value is x equal to 5, since x equal to minus 5 is not acceptable value for the logarithm base. The last case, that is log a base x equal to b. In this case, the unknown value is here. Let's see one example. Log 10 base x equal to 2. If we converted this logarithmic equation into the exponential equation, we get 10 square equal to x. This x is here. This 10 as a base of exponent, and this 2 here as a power of this exponent. So the value of x is the domain of logarithmic function. The domain of a function is a set to which the function is applied. For a logarithmic function, y equal to log x, set of all possible value of x is the domain. We can find logarithm value of only positive numbers. So the value of x must be greater than 0, that is x greater than 0. We can write the domain is x belongs to real number x greater than 0 or all the value from 0 to infinity except 0. The range of logarithmic function. The range of a function is a set that contains the image of all elements of the domain. For a logarithmic function, y equal to log x, set of all value of y is the range. We know the domain of logarithmic function is 0 to infinity except the value 0. When x tends to 0, that is x is approximate to 0, then y is approximate to minus infinity. When x tends to infinity, then y tends to also infinity. That is, when x is approximate to infinity, then y is also approximate to infinity. So the value of y is start from minus infinity and end at plus infinity. We can write the range is y belongs to real number and y is from minus infinity to plus infinity, or the whole real number, or we can write minus infinity to plus infinity. Now the graph of logarithm. For this graph we need a table where we put the value of independent variable x. We take some value of this variable x and we just put this value in that function to get the value of y. So in the first case, when x equal to 0.25, we just put this value 0.25 in place of x. When x equal to 0.5, then we put this 0.5 in place of x. When the value of x is 1, then we put this value 1 in place of x. That is log 2 base 1. When x is equal to 2, then we put this value 2 in place of x. So log 2 base 2. And finally, when x equal to 4, we just put this 4 in place of x. In the first case, when x equal to 0.25, if we put this value 0.25 in the logarithmic function, that is log 2 base 0.25, which gives the value minus 2. When x equal to 0.5, which gives the value y equal to minus 1. When x equal to 1, that case the value of y is equal to 0. When x equal to 2, that case the value of logarithm is 1. And when the value of x is 4, that case the value of log 2 base 4 is equal to 2. So we plot the point 0.25 minus 2, 0.5 minus 1 and 1, 0, 2, 1 and 4, 2 to get the graph of y equal to log 2 base x. Consider this one is a graph paper. X-axis and y-axis is indicated here. Here we just consider one small square equal to 1 unit along x-axis, also along y-axis. So first plot 0.5 minus 1. Then 1, 0. This one is the position of 1, 0. When x is equal to 1, then y is equal to 0. The next is 2, 1. When x equal to 2, then the value of y is equal to 1. Next one is 4, 2. When x equal to 4, then y equal to 2. Now we have to join all these points with a smooth line. This line represents the graph of y equal to log 2 base x. Now the characteristics of the graph. Number 1, when x equal to 1, then y equal to log 2 base 1, which is 0. So the line passing through the point 1, 0, which is true for all logarithmic graphs. Number 2, when x tends to 0, then when x tends to 0, then y tends to minus infinity. That is, when x is approximate to 0, then y is approximate to minus infinity. And number 3, when x tends to infinity, then y tends to infinity. That is, when x is approximate to infinity, in that case y is also approximate to infinity.